So today we want to welcome Michael Bowen from the Cooperative Institute for Mesoscale Meteorological Studies at the University of Oklahoma in Norman. Michael is the GOES-R liaison to the NOAA Storm Prediction Center and the Hazardous Weather Test Bed, and we're very happy to have him here today to share his expertise about the applicability of GOES-R GOES 16 for severe storms. Thanks for joining us today, Michael. We'll turn it over to you.
All right, thank you, Amy, for that introduction. So good afternoon, everyone. As she said, my name is Michael Bowen. I'm the GOES-R liaison here at the Storm Prediction Center in Norman. So I'm going to be talking to you guys a little bit today about the GOES-R series and some of its applications to severe storms and severe storm monitoring that we've noticed from improvements over the current GOES. So just a little outline for the introduction today. So I'll begin the presentation focusing on some of the improvements in satellite data from GOES 16 and the GOES-R series over current GOES data and how that improves monitoring for convective initiation and other convective applications. Also briefly talk a little bit about RGBs and some of the useful convective RGBs that are useful in convective environments. And then lastly, I'll talk a little bit about the geostationary lightning mapper, or GLM, and some of its contributions to severe weather. So first here is a little introduction to the ABI and the increase in data that the GOES-R series provides. I'm sure you have seen a little bit of this in some of the previous presentations, but I'm just going to touch on it briefly here. So there's about a 60-fold increase in the amount of data sent by the ABI compared to the current GOES 13 or 15. So the ABI acquires a full disk image 5 times faster than an imager can on the GOES 13 or 15. Spatial resolution improvement, about a four times increase in spatial resolution in the IR. Then there's about 3 times more spectral bands, 16 to 5 on the current imager. So this cube here represents the data volumes that are from present GOES in the dark orange, and then the little beige box there is the data volume from the GOES-R series. So the combination of the increased resolutions means approximately a 60-fold increase in data, and about a terabyte of data flows daily from GOES-R. So going off of that, our first question here, which upgrade on the GOES-R series of satellites regarding temporal coverage provides the most value for severe weather forecasting and monitoring in the U.S.? So A, there you have the 1-minute data. B, much improved latency. C, more frequent full disk coverage. Or D, more frequent CONUS coverage. Yeah, so I saw the results. So here's my answer, at least, just being around, from being around forecasters and talking to them, that the much improved latency has really been the biggest improvement, I think, for many in this case. So like I said, you're looking at data happening in real time and not 15 minutes old. So for the severe monitoring aspect, definitely these other, especially the 1-minute data and more frequent CONUS coverage, are also big improvements as well and are very well liked among most people. But I really feel that much improved latency has really made a big difference in how satellite data is used in severe weather applications. So let's move on quickly here, kind of shoot through some of the GLM lightning detection and severe storm application from it. So I won't spend too much time on GLM because there'll be another a presentation all about GLM later in this course where you can learn a lot more about it. But basically GLM displays 3 data values, these events, groups, and flashes. And obviously being a space-based instrument, can't distinguish between polarity or if it's CG, intercloud, cloud to cloud, those types of lightning strikes. It just detects total lightning and just detects any flash that it's able to see within the cloud. So events show the aerial extent of the lightning, and flashes show the optically weighted center point for each flash. So the way it works, all those events is every piece of light that the instrument sees, which those are grouped into other groups, which are then grouped into flashes. They're weighted optically between where the lightning is occurring in the grid boxes, so the flash would be the center point of those. So this can be useful in severe storms, and particularly for decision to support services situations, to show how far lightning can extend from the parent updraft, and that you don't have to be right under the storm to be able to have lightning strike nearby, as I'm sure most of us know. So here's kind of an example here that we have recently from the GLM. So one thing you'll notice here, one caveat with the GLM data right now that's being worked on being fixed is you see a little bit of an offset there, a little bit of a parallax issue between where the storms are and the reflectivity there and where the kind of the lightning is weighted. There's a little bit of an offset there. That's being worked on being fixed before it becomes fully operational and goes out to the public. So that'll be fixed before you're able to see the actual operational data. But here you notice here, these are the events that are all those grid boxes there. So that's showing the whole extent of lightning within the anvil there, stretching out many, many miles away from the parent updraft in this case. And in this case here, we actually had a CG strike, cloud to ground strike, and where the arrow is pointing there, that's from the NLDN VISLA ground-based network, detected a cloud to ground strike out there in the anvil, approximately 50 miles from the updraft of the storm in this case. So that's a long way from the storm, and that's a cloud to ground strike out there in the anvil. So this can be helpful in those situations, showing if that anvil is electrically charged and might have the possibility of a CG strike many miles away from the actual storm core. And then kind of one last thing here, looking at GLM, another useful application for it in severe weather monitoring is this so-called lightning jump that's been being studied for the past few years. So this is a rapid increase in total lightning. And so it's a sudden increase in the lightning production in the storm signals a good proxy for signaling that the updraft is strengthening rapidly and can be a precursor to severe weather occurring, especially if you're in an environment where you're expecting severe weather to occur and you start to see these jumps happen like this with the GLM up there in the top right of the image there. And then some of the couple of the ground-based lightning networks are on the bottom two images. They're showing CG flashes and then total flashes as well. But you see a rapid increase from about 2 flashes at the beginning of this loop to near 300 by the end of the loop. So it's a rapid increase in lightning there over just a pretty short time span. And you can see in the reflectivity there how the storm is strengthening and becoming, take on a little bit of those supercell characteristics in the reflectivity at least. So you usually see the lightning jump usually occurs a good at least a few minutes, maybe 3 to 5 minutes before you really start to see that updraft intensifying within the reflectivity core there. And with the GLM being able to update every minute, when radar scans update every 5 minutes, you get a volume scan. So you can see it. You can really see a lot of fluctuation in those 5 minutes between radar scans within the lightning data, and that can be very, very useful, especially more in a warning environment. So question number 5 here about the GLM: which of these data points does GLM not provide? Events, strikes, flashes, and groups. All right, so it looks like the majority you got that one. So strikes doesn't provide the actual, I would interpret those as cloud to ground strikes, but it provides the 3 data values that it provides are the events, groups, and flashes. All right, so just a real quick summary here we'll wrap up. So GOES-R, what we talked about today, GOES-R series provides many improvements over the current legacy satellite imagery. The noticeable increases in the temporal frequency and spatial resolution provide quite a bit of the improvements in the analysis and prediction of severe storms. A host of imagery and other derived products are also available to aid in severe storm monitoring. And the RGB composites are new to most everybody and challenging to understand at first, but there are some that may provide some unique information and improved analysis looking at the environment and also looking at storms and looking for storm initiation and evolution. Also, the increased spatial and temporal resolution makes it easier to identify features frequently associated with severe storms like overshooting tops and enhanced Vs. And the GLM will provide valuable information on a number of total flashes within a storm, the extent of lightning away from the parent updraft, like we saw, and also provide valuable information to diagnose lightning jumps, looking at the total lightning and monitoring the health and maturity of storm updrafts that way, looking at lightning data.